We're going to talk about force and acceleration today. And you're getting a condensed version of physics here. In physics, we build these ideas much more slowly and step by step. And we go into a little bit more depth than we're going to go into today. But for the purposes of this class, you really need to know these ideas here, Newton's laws, and of course to understand Newton's laws you have to understand the concept of acceleration. So, and then, one other thing, I want to start teaching you problem solving technique, and this is where we use the given, find, and solve process. And it's what was taught to me at Cal Poly, where they teach you how to set up a problem and really analyze it and look at it. It's a very simple way of doing it, but it does make things very, very clear. So I'm going to be going through that with you. So let's begin. First of all, Newton's laws, named after Sir Isaac Newton. He developed these laws in the late 1600s. And it is no coincidence at all that the Industrial Revolution began soon after he came up with these laws. Because before Newton, we had only craftsmanship. We didn't have engineering. We had craftsmen. We had people that were really good at building things and making things, but all of it was based on trial and error and experience. None of it, the people were building machines or whatever. They were very primitive, and nobody did any engineering. Because engineering is the application of our knowledge of the universe to solving technical problems. Well, they didn't know anything about the universe, not really, not in any systemic kind of way. And so Newton changed that. I mean, Galileo kind of got it started, and Kepler got it started, and some people earlier than Newton, about 100 years before Newton, it kind of got started, but Newton put it all together in a beautiful statement of laws that are very simple and extraordinarily profound and useful. Okay? And some of them are so basic, you think, well, why didn't anybody think of this before? Well, the reason is that, Europe, many other cultures are very smart people, but they didn't write it down. And in the European cultures, they were so hung up on Aristotle and mysticism that they just it's almost like they were deliberately ignorant. I mean, they were purposefully ignorant. So Newton drew the curtain back on all this, and because of him, we can now do mechanical engineering, and because people could then do mechanical engineering, that's when the Industrial Revolution began. So this is really as profound and important as it gets. So, speaking of profound and important, here is an object, and this object is what we call at rest. So it is not moving with respect to my reference frame. My reference frame here is the piece of paper. We're going to say with respect to the piece of paper, which is at rest, this little toy is at rest. Now, are we really at rest? Are we really at rest here on the Earth's surface? No, the Earth is rotating about its axis, and it's circling the sun, and of course the sun is on a 250 million year trip around the galaxy, and our galaxy is in motion compared to other galaxies and so on. But let's not get too cosmic here, okay? Compared to us sitting here, this piece of paper is not moving, and we're going to call the piece of paper here our reference frame. We're going to refer all motion to it, and we're saying that it's so. Therefore, the toy and the piece of paper are not moving with respect to each other. And since the paper is our reference frame, we're saying that the toy is at rest. Simple. Now, what if we wanted it to move? Well, I would have to, let me zoom here. I have to apply a force to it. Okay? A force was applied. And that's the only way to get it to move. You have to have some kind of net external force applied to the object in order to make it move. It will stay at rest unless something forces it to move. And that's really Newton's first law. Now, there's various ways of saying Newton's first law, but the way I like to say it is objects don't change the way they are moving unless you force them to. Okay? Unless you force them to. Things don't change the way they're moving unless you force them to. Did you have a quick question for me? Or? Oh, okay. So, this guy's at rest. In order to change that, boom, I got to apply a force. Now, what if it actually got it moving? Okay, now you have to use your imagination here because I can't demonstrate this under a document camera. But what if I was in outer space and there was no planets or anything around me, quite lonely, and I was wearing a spacesuit, thank goodness. But I've got this toy in my gloved hand and I throw it. So now the toy is drifting through space. Okay? It's going to continue drifting through space, moving in the same direction at the same speed, unless what? We force it to change. It runs into a planet's gravity, sucks it in, or it hits an asteroid or something, or maybe it's got a jet on it and it throws mass the other way, so it pushes itself forward. Okay, but you got to do something to change its motion. So this isn't just about being at rest, although that's the easiest example to show. This thing's going to stay at rest unless you force it to move. But if, let's say it's in motion, if you want to change its motion, you have to apply a force to it. Now, changing motion, that includes going in a circle, right? Going in a circle is changing its motion. It's changing the direction it's going in. So you need a force to do that. Or if it's moving and you want it to slow down, it takes a force to do that. Or if you want it to speed up, it takes a force to do that. So you have to force it to. Now that's all that Newton said with the first law, and it was kind of Galileo who came up with it. This is called the law of inertia. Okay, it's the law of inertia. And, things that have inertia don't change the way they're moving unless you force it to. Now, inertia is the same thing as saying mass, which we're going to get to next. Okay, it's kind of a simple idea, really. Although, here's what they used to think. In Aristotle and all those people, they thought, okay, something's moving. What happens eventually? It'll eventually stop. That's what everybody observed. And so they thought, the natural condition of all objects is to be at rest. That's what they thought. That's why they thought that the earth had to be the center of the universe, because the earth was at rest and everything wants to be at rest. And that there was no way the earth could rotate or move around the sun, because then it wouldn't be at rest. It would eventually stop. So they were wrong. Okay? But it was Galileo who kind of first figured out, hey, once you get something going, it's probably going to keep going unless some kind of outside force is exerted to it. Okay, take physics and you'll get that in more detail. Second law. The second law is really a a more mathematical statement of the first law. It says, and it states how objects will change. Objects, if you are going to change the motion of an object, you are going to, if you're going to accelerate the object or decelerate the object, you got to apply a force to it, and so it says that. Well, actually, you know what? To save time, because this is going on too long, I'm just going to give the equation for it. Here's the force an object you apply to an object. And a force, as we said last time, a force is just a push or a pull. Sometimes the objects are in contact, like my finger in the car, but if I hold the car up here and let go of it, oof, down it goes. Even though it wasn't touching it, it's a gravitational force at a distance. Force will cause objects to accelerate, or acceleration. And we're going to define that. Acceleration is the rate at which an object is changing how fast it's going. Okay? So that's acceleration. Now, how much acceleration you get depends on how much inertia this has. I think you would agree if this car was made out of lead, it would be much harder to get it up to speed. I'd have to apply a greater force to it, wouldn't I, than this one, because it's just made out of foam. Right? So this is very light for its size. This doesn't have a lot of mass, or it doesn't have a lot of inertia to it. So a little bit of force gives me a lot of acceleration. But if I made this out of lead, I could make it accelerate. I just have to push on it a lot harder. So really, the amount of acceleration I get for my force depends on its mass. Mass. Mass is another word for inertia. These guys are kind of the same idea. Now, if I double the mass on an object, to get it to accelerate, I got to double the force. In other words, force and mass are directly proportional. If I double one, keep the other the same, I got to double the other one. That make sense? You following? You with me? You with me back there? Okay. So force equals mass times acceleration. So, and we express it like this. F for force equals m for mass, and then we use the letter a for acceleration. F equals ma. Now we're gonna put vector hats on it. We're gonna talk about vectors later on. But F equals ma. The force you need to cause an object to accelerate depends on the mass. It really almost defines what mass is. Mass is how hard it is to make an object accelerate. This little equation right here is the most important equation in physics. F equals ma. Oh, E equals mc squared gets all the glory. Okay? But F equals ma delivers the goods. Okay? We were well into the Industrial Revolution and all that, and all the engineering was doing quite well without E equals mc squared. Engineering did not exist before F equals ma. Okay? So this is a basic equation that we're going to use. Now I want to talk a little bit about the units we use. And could you hand me one of those brass masses right there? Thanks. And happy birthday, Evan. All right. So this right here, this amount of stuff, this is 1 kilogram of mass. Now, how did they decide how much stuff was a kilogram of mass? I don't know. That's the French. The metric system and all that. They had there's a slug. There's this big slug of, I don't know what it's made out of, platinum or something, that defines what a kilogram is. So now we use, in this class we define a kilogram to be this sad looking thing. And it has inertia. Ugh. It's not, now if I do this, I feel its weight. Okay, Earth's gravity is pulling it down. But if I want to feel its inertia, I just got to shake it. Shake it. Oh, shake it. Oh, sorry, Anthony. Anyway, yeah, I can feel how hard it is to move this thing back and forth. Okay, that's its inertia. Like this thing, oh, it's easy to move this back and forth. It doesn't have very much inertia. But this thing, oh, I'm going to put my arm out of its socket, okay? It's got so much inertia. So how hard it is to move something back and forth, that's a measure of how much inertia it has. That's a measure of its mass. This is 1 kilogram of mass. So in the metric system, we use kilograms. Okay? Now here's where this class is getting kind of, we're taking some shortcuts here. Okay? Acceleration. We need to talk about what acceleration is. Okay. So acceleration. And I'm recording this, so I'm just going to blow through it. Okay. All right. Acceleration. Oops. There we go. It's defined to be the rate at which an object changes its velocity. Now in physics, okay, right now in regular physics, we're still defining what velocity is, and we're going really slow. Now in AP physics, we've already talked about acceleration and all that sort of thing. So you guys that aren't in either one of those classes, you got to really pay attention right now and put your thinking cap on. All right. So if I have an object that's moving, let's say I open my eyes and the object is right here, and then I open my eyes and the object's right here, and then I open my eyes again and take a look, and then the object's over here, and then the object is over here. Let's say every second I'm looking where that object is. Does that make sense? An object is moving. It's just, somebody's walking along the sidewalk or something. Okay? And this dot represents that's something, and it's moving. Yes? It's moving. And let's say that we're doing it like this is at t for time equals 0. That's 0. And then this is 1 second, 2 seconds, 3 seconds. S for seconds, 4 seconds. Okay? And let's say that they went from this distance, they went 8 meters. You know how far 8 meters is? Okay. Well, it's about from group 1 over to group 4. That's about 8 meters or so. Okay. About 2/3 the length of this room is about 8 meters. 8 yards, a little over 8 yards. Okay. Not very far. Now, so how fast is this person walking? If it takes them 4 seconds to go 8 meters, how fast are they going? How far are they going every second? 2 meters. So you agree with that? So we call that velocity. V for velocity. Okay, equals how far I go, which I call displacement, but I don't want to get too crazy here, so I'm just going to say, we'll just say distance for now. This is kind of a lie, but distance over time. Well, what distance did I go? 8 meters over 4 seconds. So this person is walking 2 meters per second. And if you watch me walking around campus, I walk almost, because I walk fast. You people walk so slow, it drives me nuts. I can't even stand watching you walk slow. Huh?
I walk fast too. I get stuck on all it.
Yeah, come on, people, move. I got places to go. All right, so this is called velocity. So the velocity v equals 2 meters per second. Well, what is acceleration? Acceleration is the rate at which I increase this. Now this person right here is just going 2 meters, 2 meters, 2 meters, 2 meters. They're moving with a constant velocity. But what if, they had to start up with something. What if the person's doing something like this? They start here, and then you see him 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 here, and this person's walking faster and faster and faster and faster. So let's say that every second somebody's increasing their velocity by 2 meters per second. Now, you would have to be in a car or something to do this. You couldn't do this on foot for very long. So I'm going to say that acceleration is, well, you guys have all seen this little delta symbol before, right? What does this little delta mean? Yeah, even you non-physics people, you've seen that before? That means delta. That means how much I changed. Okay? Right? Change. Change in what? Change in velocity. It's how much I changed my velocity. Now, what else changes? I mean, we live through it all the time. Time. It's how much you change your velocity over a given change in time. So this right here defines acceleration. It's the rate at which I change my velocity. Now you've heard of this before, right? The Tesla Model S goes 0 to 60 in 3.8 seconds. Okay? That is a form of acceleration. 0 to 60, that's a delta V. 3.8 seconds, that's a delta T. Yes? The units are kind of weird there, though. Although they're perfectly okay for comparing how fast cars accelerate. But what we're going to do is this. Let's do an example. So here's an example. A car increases its velocity from 10 meters per second to 30 meters per second in 5 seconds. What is its acceleration? Okay. You got that copied down? Okay. I'm now going to show you the problem-solving technique I want you to use in this class. It's very simple. You may usually, like if it's a textbook problem or a worksheet problem, you don't have to copy this down. But I want you to use given. You write the word given. You write the whole word given. The underline it, I don't know, colon, that's good. Now, what's happening here? We've got a car. Here's my car. Right? Looks just like my car. And its initial velocity, I'll call it V initial. Oh, I'm almost off screen. Yeah. Is equal to, well, what did I say in the problem? 10 meters per second. That means in 1 second it's going to go 10 meters. Now later on we look at it, whoops, and it changed shape, I don't know why. But its final velocity, you see that the I means initial and the F means final? Its final velocity is what? 30 meters per second. Now what is the delta T to get here? How much time went by? 5 seconds. So now we want to find, then you write the word find. Given, find, solve. We're trying to find the acceleration. Solve. Okay, we have an equation that describes acceleration, that defines acceleration. Acceleration is defined to be how much I changed my velocity over how much time it took to change that velocity. Do you see how I'm saying that out loud? I say what the thing is. I try not to say delta V over delta T, because then you start losing the meaning of it. If you say to yourself, the acceleration is how much I changed my velocity divided by how much time it took. That's the time rate at which we change velocity. So how much did I change my velocity? Now look at the problem. This one's easy. How much did I change my velocity? If I go from 10 to 30 meters per second, how much do I change? 20. Now how did you get that? Didn't you went 30 minus 10 is 20? Okay. So what you do to find how much something changed is you say, well, where did it end up? Subtract from it where you started. Right? Now you could do the same thing for time. What's the final time minus the initial time? But that's a little bit crazy for what we're doing. Well, what's the final? Was 30 minus the initial velocity was 10. Now t final minus t. Well, I'm just going to say that 5 seconds went by. Now, do you have to go through this? If I was going to do this in my homework, I don't know if I'd say delta V. I would put the 30 minus the 10, but I don't. You don't have to really go through all that. If you know what delta means, okay. So now we have the acceleration is equal to 20 meters per second divided by 5 seconds. Well, 20 divided by 5 is, oh good, you know something. All right, 4. And then what's a meter per second for every second? So we're increasing 4 meters per second every second. See how I wrote those units? It's perfectly okay to leave the units like that, because that's what the units of acceleration are. It's how much I changed my velocity per unit time. How many meters per second I increased every second. Does that make sense? Now, here's what you'll see in textbooks and everything, and I'll even do it because it's a shortcut. This is like a compound fraction. This is like a meter per second times a 1 over seconds. You agree with that? Like a compound, you know. And so they'll get, oh, this is a meter per second squared. And so people will write for acceleration, meters per second squared. And then people who are doing this for the first time go, what the heck is a square second? I don't know. There's no such thing as a square second. It's just a shortcut for saying this. It's how much I increase my velocity every second. It's not a square second. Dimensionally it is, but you know what is actually really happening, meters per second every second is good. If you want to write this, I'll let you. But this is actually what's happening. Yes? Questions? Okay. All right, so that's my answer. I have solved the problem. So this is how you would set up a problem like this in your homework, is you say, given, find, and solve. And by the way, if you're doing a robot design or you're trying to solve some kind of problem, it's very often convenient to set up, okay, draw a picture of your problem, what do I know, and very clearly state what it is that I need to find out. And if you clearly state a problem like that, your whole problem-solving process works a lot more efficiently. You'll get to the right answer faster. So good problem-solving technique, very important. Now, and notice that I started off with my basic equation that related what was given to what I'm trying to find out. Okay? You guys are sick of word problems in math? Use given, find, and solve. It'll make it easier in your math classes. Okay. Now, what if I told you this? I'm going to add something. So, if the mass of the car was, let's make it like a go-kart or something, 100 kilograms. That's a pretty light car. Like one of our, robots. Our robots are about 60 kilograms. What net force was needed? Okay. So let's say I added that to the problem. Well, then what I'm going to do over here, under given, I'm going to put the mass was 100 kilograms. And then what else am I trying to find? I have to find the acceleration, but I'm also trying to find the net force, which I'll call F for right now. Well, the net force, there I went and called it net force. So the net force, the force that causes something to accelerate is often called the net force. So I'll just call it F for right now. The force is equal to mass times acceleration. So the mass is 100 kilograms, and the acceleration was 4 meters per second every second. And so the force is equal to, well, what's 100 times 4? 400 in most countries. Now, what's a kilogram meter per second per second? Yeah. Well, we don't want to, we could write that. Kilogram meter per second squared. I'll go ahead and do that. I could write that and that'd be fine. Because the force is defined to be how much acceleration you get, when you apply it to a certain mass. So it's mass and... But this has a name. We combine all those units into something called a Newton, named after Sir Isaac himself. Okay, and we abbreviate it with a capital N. So this is 400 newtons. That's my answer. It took 400 newtons to make a 100 kilogram car accelerate at 4 meters per second every second. Okay? So let's summarize and then we'll work a few problems. Now, we didn't get to Newton's third law today, but that's a whole separate thing. So I just want you to be able to deal with force and acceleration today. We have acceleration is defined to be how much I change my velocity over a given span of time. And force, Newton's second law, the force on that object will cause that object to accelerate, but the amount of acceleration depends on its inertia, which we call mass. And so you will use these equations to solve problems using the given, find, and solve format. And I just happen to have some problems for you to solve using that. So get some practice. Any questions? That is all.